Yes, so we are on. So welcome to the session, session 10. It's been a long journey, since we started with, was it semi-groups we started with? No, what did we start with? We started with semi-groups, right?
Sets with closed binary operations.
Okay, yeah. Yeah, from, starting from there, we built up the stuff, our knowledge base, and we are now in lecture 10. I hope, by the way, you enjoyed the coverage of cyclic groups, and you had some sort of a flavor to see how they, they are very useful in things like cryptography, for instance. So yeah, you definitely have the basis to study cryptographic systems with the underlying mathematics is discrete logarithm problem. Yeah, these are like not just the Diffie-Hellman, but elliptic curve cryptography, because that also uses a cyclic group. So yeah, Amir saying that was good. Thanks. Yeah, there were some minor corrections I did in terms of the parameters on the study sessions. The thing in about the choice of the prime number and these things, but it doesn't matter. In general, the abstract framework is okay. It gave you a bit of understanding about how the protocol works using something that you learn, notion of a cyclic group, the generator, and the basic fact of the property of the exponentiation that you know how to do. So yeah, so anyway, I hope it was very, very useful. So today, as you can see, we are only covering very, very minimal today. So we'll start with symmetric groups over sets. Actually, before that, I will just we'll go through the normal stuff, like the course approach stuff, just for those new people joining us. And I will make a brief comment on the recently announced NIST post-quantum cryptographic standardization proposals. They propose some stuff. I'll share the article. I think some of you must have seen the newsletter, so just go through it. It's very interesting times we live in. So yeah, so before that, this is where we are, lecture 10. I think we should be able to clean up this crash course in lecture 16, I think. Let's see how it goes. Depends if we spend too much time on symmetric groups. Well, maybe not, but maybe if we tailor the symmetric groups to we start moving towards matrix groups, then it's natural that because the last part of it is really to cover the basics of matrix groups, really. So that's the final thing, because they are the prototypes of the Lie groups that we will be interested in the next module. So yeah, so we are here. Finger crossed we can do it in 16 sessions. Before that, we had this on topology and differential geometry. The reason for that is because after the current crash course on group theory, we will go to Lie groups and representation theory. Obviously, Lie groups are not just algebraic structure, right? They have a smooth structure. So in order to understand that, you need to understand a bit of differential geometry. So that's why we did the topology and differential geometry crash course. So as far as this crash course goes, so we started with semi-groups, we went to monoids. We are here in the group section. We covered a specific type of groups called cyclic groups last time. Today we will cover we'll start covering other special type of groups, symmetric groups. And then hopefully we get to this matrix group section as soon as possible, because this is the end of this crash course. So you have your mind a little bit fresh. We cover some of these basic important groups for the Lie group and representation theory module, like the orthogonal group, the special orthogonal group, the same with the unitary group and the special unitary group. All these are prototypes of Lie groups. And then after we do that, hopefully, maybe we'll, I don't know, people, it depends on your availability. You know, I can carry on. Whether we should take a break for people to refresh, especially with the differential topology and differential geometry stuff, because you really need to understand what a manifold is, you know, I mean, a smooth manifold is, because otherwise you will struggle. So, I mean, I have impression maybe by latest end of August, we should be able to wrap this crash course, wrap it up. Yeah. So maybe in that case, maybe we should start the Lie groups and the representation theory sometimes in September, maybe towards the end of it, just like around the time we started the foundation module. I'll send a survey. Yeah. Just give me a second. I forgot to plug my laptop, so my battery is running flat. All right, I'm back. Okay, so yeah, so I'll send a survey to see, you know, what are people's availability and these things. And we will do something very special, interesting. I mean, in the time when we get to Lie groups and representation theory, it will be much more tutorial oriented. So I'll get some of the grads from our company to be, you know, holding tutorial sessions. This is also a way of them connecting to people who are already in the industry. These are like young mathematicians looking to come into the industry. So we'll have people, maybe one or two guys with a background in relevant to this, to the crash course, to be, you know, organizing a study session, you know, go through tutorials, exercises, and these things, because this will be very useful, especially when we go through the applied stuff, like, you know, we talk about quantum error corrections and these other stuff. So it's good that you have like a hands-on concrete practice with the concrete structures, and, you know, feel comfortable proving stuff and these things. So, and making constructions. And that only comes obviously with the practice. The more you have, the better. Okay, so I hope I didn't make, this is a comment I wanted to say. You know, you saw this this week actually was very historic in cryptography, right? You know, for example, public key cryptography is really based in two problems, really. You know, one is prime factoring. For example, the RSA relies on this in order to, you know, to guarantee the security. The other one is the discrete logarithm problem. You know, for example, the Diffie-Hellman key exchange, you know, El-Gamal, and so on. And then the other, the extended discrete logarithm problem, in the sense of being discrete elliptic curve discrete logarithm problem. So this is the discrete logarithm problem formulated in the context of elliptic curves. You know, elliptic curves, there is a group associated with them, a very interesting group that hopefully at some point we will have a crash course on discrete logarithm cryptography, actually. So I'll invite everyone who is interested in this. You already understand the classical Diffie-Hellman thing. And then hopefully it's guaranteed that we'll cover elliptic curve cryptography, so you will be able to understand this. Yeah, so everyone is invited. I'm working on the program for that, trying to get the stuff, the schedule right, but it will probably be in parallel with something else. But, you know, as these things happen, sometimes you have to do two things at the same time. So you are most welcome to join. Yeah. So anyway, so all these guys are these cryptographic systems are vulnerable to quantum computers. The Shor's algorithm in particular. So that means that people have been thinking about post-quantum cryptographic systems. You know, try to devise something that existing quantum algorithms like Shor's algorithm cannot break. You know, so there have been quite a few interesting proposals over the past few years. You know, very, very clever people And finally, the NIST, the National Institute of Standards in the United States, over the past few days, they propose these guys as the first set of standards. There are others that they will push forward until I think towards the end of the year they will decide to the next phase. But this is a very good timing, because this essentially enables one to, companies now over the next coming months and years will be looking into, studying these cryptographic schemes, not just on the theoretical side to try to, mathematically attack them to make them better, but also derive other stuff, other systems out of them. And also on the implementation side to, try to find, effective ways of, implementing them. Yeah, so there's a huge opportunity in this field in the sense of, moving existing projects, whether open source or, proprietary stuff into these new cryptographic systems. So there's a huge opportunity here for, those of you who are coming into quantum computation and, you want to go through it. This type of this is actually a very interesting area as an entry point, because there is demand, not many people. Obviously, it's very important to know the underlying mathematics of this. So we will be doing a lot in the next coming months in focusing on not just classical cryptography, but also these other stuff. This brings me to the next slide that I wanted to, as you can see, I forgot. This is one that I said I forgot to add what I wanted to add. So all I wanted to say actually, amongst other things, is that once in parallel with the thing, or probably after the courses on cryptography, the main courses, we will start having study group sessions on post-quantum cryptography, in particular, analyzing these existing, the recently proposed cryptographic systems. Yeah, so members of the community, you guys, you are most welcome to join and listen. We'll have like mathematicians come in and do a presentation, cryptographer, and this type of stuff to go through each of the protocols and have some insights to share. Okay, so yeah, that's all I wanted to say, share. Don't worry, we'll finish on time, because we will not cover that much anyway. Okay, so that's all I wanted to cover. Blank slide. Okay, so let's crack on. So everyone can see the slides. Okay, so let's start with the first definition. So given a non-empty set X, we denote the set of all bijections sim of X. So sim of X contains all the maps from X to itself that are bijective. Okay, so another on a notation point of view. By the way, can you see the pointer, George? Is the pointer when I do this?
I don't see it. Let me increase the.
Is everyone else? Can everyone else see the pointer?
No.
No. There's something thing with the Crowdcast is I've told them the I gave him the, let's see, open menu. Okay, so I need to turn the pointer on. I didn't know. What about now?
Now I see it.
Okay. Well, they yes, yeah, but it's still like I just wanted the mouse. It's much more thin than this this red stuff. Let's see if I can change the color. Well, my football club is red, but it's just a little bit thing to. Let's see, pointer. Well, it doesn't give the option. Yeah, I don't have time to find out anyway. So at least there is a pointer. Yeah. Okay. So I was just saying this. Instead of this, very often authors use this sim of X, subscript X, instead of this. And another convention that is often, you will see this a lot if you pick a book in the literature, is that when X is finite with cardinality n, then we use the notation xn instead of this xn. instead of sim of x. Now, another thing you will notice is I claim that the composition under the composition of maps is it defines a binary operation in the set, right? Meaning that if you have two maps, right, two bijections, then their composition is again a bijection. Correct? We are on the same page, right? Okay, so red gets out attention. So are you saying you prefer if I turn off the pointer? Because actually it's very distracting for me as well. Anyone else like a similar situation as Berend? Berend, what I understand is that the pointer is distracting. Yeah, the problem I have is on the settings there is nothing to say change colors. Let's see more.
I would say with what you're most comfortable with.
Yeah, I will turn it off.
If it maybe becomes unclear, kind of indicate verbally where you are on the page.
Yeah. Okay. Yeah. Yeah. So so there's no doubt that this sim of x, the composition of maps is a binary operation on it, right? And even more, I claim you will be able to prove this, that under the composition of maps, sim of x forms a group, and the identity map is the group coincides with the group identity. Okay, so this is a homework for you guys. I claim you can solve this. Now, here's a cheeky question: is whether in general sim of x is abelian or non-abelian. What do the people think? Don't feel shy. The thing, just non-abelian, okay?
I think for n sufficiently small, it can be abelian.
Mm-hmm. So we have consensus. Yeah. Yes, that's right. That's right. We will see this in a thing. So it's non-abelian. So we have a consensus. Okay. Now, let's see some concrete examples with the finite. I'm so sorry because this is so small, but I hope you can see. The diagrams is a little bit small. I'm happy to share this, give Google Slide link so you can, zoom in if it's easier for you. Does anyone want the slides to look at it, or can you see?
I can see if I go to full screen, and then I just have to get off full screen to monitor the chat.
Yeah. So yeah, sorry for that. It's because I couldn't make these things small. As you can see, this a bit of thing drawing them. Yeah. So let's X be a finite set, consistent of 1, 2, 3, right? Then by convention, sim of X is, as we were saying, is let's call it S3. Okay, not S3 like the Amazon bucket. I know we have some developers on the thing in the audience, some infra people. So S3, this is the mathematician's S3, not the Amazon S3. And this, you will see a generalization of this. I mean, you should be able to see this as well. It has 6 elements, which means in this case we got there because the number of bijections or permutations in any finite set is, if the set has an n element, is a factorial of n. Okay, in this case it has 3 elements, or the factorial of 3, right? So this exclamation mark is factorial. This stuff that we learn in kindergarten, high school or something. I don't even remember when the factorial is introduced. So that's the thing, and I hope I got it correct, right? The factorial of 3 is 6, right? Correct. So let's try to identify some elements of S3. Okay, so first we have the identity. The identity defined like this, like it takes IDX of 1 equals 1, IDX of 2 equals 2, IDX of 3 equals 3. So the identity, as obviously you know, does nothing. Leaves the elements unchanged. Okay. So this is a way of doing it. Another way, this is much more common in the thing, this notation called two-line notation. By the way, without arrows, I'm putting here the arrows just to make it easy for you. In general, in textbooks, these arrows don't show up. So in this case, in the identity map, we could use this notation to, instead of expressing this, to do this. So 1 goes to 1, 2 goes to 2, and 3 goes to 2. 3 goes to 3. Okay. So just follow the arrows. It goes from up downwards. So you line up the elements of the set, and then downward arrow you define your permutations. Okay, so that's the identity. Another one we can do is sigma 1. So I call it sigma 1. It could have been something else. So say for example we have sigma 1. Sigma 1 of 1 equals 2, sigma 1 of 2 equals 1, sigma 1 of 3 equals 3. Okay, again, we can do the same strategy here. We can use the two-line notation by making it this way. So sigma 1, this map will be defined like this. So 1 is transformed into 2, 2 is transformed into 1, 3 into 3, so 3 is unchanged. Okay, so this is sigma 1. The same, we can do another map that I call sigma 2, that's defined like this. So it's like 1 goes to 1, 2 goes to 3, 3 goes to 2. Okay. There's another notation that we'll touch in the next session. Is called the cyclic notation. It's a little bit more thing. Don't worry with that for the time being until we get there. But this is just one of those things that you have to feel comfortable with when we are dealing with finite sets. These things they will show up again. Well, I chose them arbitrarily, but they are elements. These are elements of this. So these are elements of the thing. These are permutations. These are bijections on the set. They are not arbitrary. They are arbitrary in one sense, but they are bijections. So they are part of this the group. They are group elements. So these are part of this S3 under composition of maps. I could have chosen. In fact, one of the challenges is for you guys to. So far, I've pointed for three of them. So the challenge is for you guys to find the remaining ones. So that's the S3 challenge. So the first challenge is identify the remaining elements of S3 using the two-line notation without the arrows. I mean, you can use the arrows if it's helpful. But in the textbooks, just be aware that the arrows are normally not used. I'm using the arrows just to make it easy for you guys to follow. And another challenge is compute the composition of sigma 1 with sigma 2. Okay, and then compute the square of sigma 1, the cube of sigma 1, the square of sigma 2, and then the cube of power the cube of this. They say the cube. I'm not even saying whether maybe the language the power of 3. Maybe this is much more cleaner. Okay, so and then the other thing I want you to do is to find the inverse of sigma 1 and the inverse of sigma 2. Obviously, for this, it will be helpful for you to identify all the group elements. That's why we are using this toy example, because you have less. You have only 6 elements. So I've given you 3. You have to find the remaining 3. That's one of the reasons we are not covering that much, so you can have time and go think about this. And another challenge is to find at least a non-trivial subgroup of S3. Okay, you know what a subgroup is. This is, again, you have to go and revise the definition of a subgroup. So, and even better, can you identify all the non-trivial subgroups? Okay, by non-trivial I mean because obviously the set with the identity itself is a group, not that one, not the set with not the group with only identity. Anything else, and also the entire thing. Obviously, the entire S3 is also trivial. So any proper subset, that's also a subgroup. Okay. And then when you identify the non-trivial subgroup of S3, we know that, first of all, do you agree that S3 cannot be cyclic? Can anyone, does anyone have any doubts why it cannot be cyclic? Do you agree? S3 cannot be cyclic. So S3 is not a cyclic group.
Yeah, I don't see how any one element can be a generator.
There's another way of seeing that too, because of the isomorphisms. Well, it's a group, Amir. S3 is a group, so certainly everything has an inverse. Remember, a cyclic, it needs a generator. You can think another the quickest way to get there is to the thing in my point of view is just the isomorphism theorems. Remember, every finite cyclic group has to be isomorphic to what? And when two things are isomorphic, it means they have the same structure, right? So, for example, an abelian group, S3 is non-abelian, so it cannot be isomorphic to an abelian group. Okay, so maybe think about it. Go and think about it. Yeah. So indeed, S3 is not cyclic group. Now, something not being a cyclic group, it doesn't mean that it might not contain a subgroup that's abelian that is cyclic. So this is the question. The thing, in this case, you'll verify by if you identify all the cyclic groups of S3 and check, maybe one of them, one of them might be cyclic, maybe another one might, maybe they are not cyclic, all of them, and maybe if you increase, you go instead of S3, for example, we'll see another example, which is S4 or S5, S7, and so on. You might be lucky, Let's see. Okay, so try to go through all this. That's one of the reasons I'm not covering that much today, is for you to go and really get your head around these things, because this connects the new content with the past content, with the past notions that that's fresh in your mind. Okay, and the second challenge, this one is interesting, a little bit trickier, is let's suppose we have this set H3 defined as a set of all sigmas in S3 such that sigma of 3 equals 3. So you go and look at the sigmas, right? The group elements of S3, and then you see the ones that when you apply them to 3 generates 3. Whether that set, those guys, whether they form a subgroup of S3. And the question is, after that, if that's the case, if H3 is a subgroup, whether it's cyclic. Okay, that's the natural question. Okay, so that's the challenge one. I mean, S3 challenge. Let's go to the next one, the next concrete example. So the next concrete example, we have this set X made of 1, 2, 3, 4. So we had added an extra element. And you can see already, this means that this has 24 elements, right? The factorial of 4 equals 24. I hope I got it right. So again, the same playbook, the identity, we have, sorry. Okay, I realize I forgot one slide, but I will add it before we finish because it's very important. For the time being, we'll go through this. So in this case here, like we have S4. We have this, right? Why is this slide not? Yeah, so we have the same playbook. We have IDX, the identity, which takes 1 to 1, takes every element to itself. And then we have sigma 1, defined like this, takes 1 to 3, 2 to 2, 3 to 1, 4 to 4, and then sigma 2. Okay, we have this. So the other challenge is similar to this one, but I didn't add this on the slide, so I will add it now. So for the time being, let's see, let me go back. Any comments on the chat while I do this, George? Sorry for that. I think I deleted this slide by mistake. Yeah, so it should appear now. Now what I need to do is to find the other slide. Just bear with me, please. Because I need these two. Any other comment, George, you want to do while I correct this? This is the thing. I promise. Am I still on, by the way? I'm just on another screen.
Amir has a question. Are the sigmas arbitrary?
Yes, they are. I chose them arbitrarily, but they are, elements of the the group of of the S's. So they are group elements of the thing. In this case of S4.
I think the arbitrariness is saying is labeling them sigma 1, sigma 2, and so forth as arbitrary.
Yeah. I mean, like, yeah. So I could have labeled them something else. That's right. Was there any other question while I just finalize this? We should be good to go. Sorry for that. But it's very important to go and revise this thing because it's especially when we start moving towards much more complicated stuff.
So Berend is asking, so for group of size n, there are n factorial mappings.
Yes, correct. Yeah, so that's good. You already figured it out. Yeah, it generalizes to n. Yeah, so the larger the n, the more headache for you to try to find them, to do them. That's why I stuck to the thing, to the toy stuff.
And
I started. Yeah, go ahead.
That might also be an implicit little challenge to show that n factorial is the number of mappings for a finite n.
Yeah. Yeah, that's right. I think I have a duplicate here. Let me take it out. Yeah, so any doubts on these notions of the thing? So nobody has any problems with this, So the challenge then, the next challenge is similar to the challenge with the S3. Okay, so I think this thing needs to refresh. I need to refresh this. Why is it not showing? I think I have to stop sharing, and sorry for that. Okay, yeah. So I'll share again. Copy. Let me go. Okay, it's screen. Tab. Yep. The slide is back again. So we were here. Yeah. Can you see this, George? Somehow, why this slide is not?
Okay, I see it. Well, I saw a new slide flicker by.
Okay. What I will do is, let me just, this is a bit annoying. Sorry for that. Only 2 slides, but they are important. Let me download it and upload it. We don't have the pointer anyway, so I will just download it. In the meantime, is there anything, any pending question, anything?
All quiet on the Western chat.
Okay, let's see. It's uploading. It's probably to do with the caching stuff with the other. Normally, people start when, talking about these things with things like, by drawing things like, triangles and these things and all this stuff. And we'll come to that. So today I started really abstract rather than, because this is really just encoding a very intuitive notion that we all have, the notion of a symmetry of an object, really, things that leave an object unchanged. For example, imagine this sphere. For example, what can you do? What does what things leave the sphere unchanged to your eyes, to your naked eyes? If you have a sphere here, what if you do some action? What sort of action you can do on it, and still it looks the same, as if nothing has changed. So this is just encoding it. Let's see. S4. There you go. S4 challenge. This is what we wanted. Yeah. So I hope you can see. Let me maximize this. Actually, I have impression that uploading this, you can see better, right?
Yes, actually, this is a little clearer.
Okay, so I will start uploading it, even though we didn't have the pointer. That's fine. It looks better. Okay. Let's see. Yeah. So the challenge 4 is a similar thing. Okay. I've given you some 3 elements, randomly chosen, but chosen out of out of the group itself, S4, right? So there are 24 of them. So I'm not going to ask you. Am I actually asking you to actually forget this? Identify the remaining elements of S4. you don't have to do this. I will be happy if you can identify, let's say, at least 4 of them, because there are like 24. I doubt you will have time to, but it would be, if you have time to go through and do this, it's a great exercise for your mind, really. You know, it's like playing Sudoku. It has the same effect. So yeah, so try to identify. Or yeah, go ahead, George.
With 24 elements, it's not unreasonable to do the full multiplication table by hand and maybe see some of the patterns.
Yeah, actually, it helps you. That's a good point, because the larger, the more you should be able to see the patterns. Especially, it also gives you the option, because one of the questions I will ask you here is for you to identify, you know, non-trivial subgroups, and then I'm asking whether any of the identified subgroups are cyclic, right?
Yeah.
So the more, you know, if you are able to do all of the elements, identify all of them in a big piece of paper, you know, you should be able to, life will be easier for you in terms of constructing subgroups, giving examples of non-trivial subgroups of S4. Okay, so yeah, so similar challenges as the previous one. The only thing, obviously, this is a bigger group, right? And actually, it will be interesting for you to see the actions of some of these elements, you know, see some patterns comparing to some elements of S3, for instance. Yeah. Okay. So challenge 2 is similar, in similar fashion. H4 is a set of all the elements of S4 such that sigmas, such as sigma of 4 equals 4. The question again, the similar thing, is whether H4 is a subgroup of S4. Now, as just like Behrend, you know, could generalize in terms of you know, the permutation stuff, the number of elements. If this is all true, you will start to see a pattern. Then you can see that if for any n, Hn, you know, for any Sn, then based on the answer, it should be the same. In principle, unless, you know, the nature of the integer also matters, you know, whether, for example, it's prime or not. But this should give you a decent indication. Okay. Is there any question on the chat? Because I'm on full screen, so I cannot see. I can minimize and look at the chat. We only have one more slide to go, and then that's it. Okay, so I'll proceed to the next slide. So this is, I call it food for thought. I hope I didn't make any typo. So what I want to say is that, as you probably already figured it out, you know, studying like sets by themselves is always boring. What you want is always to add some extra structure in the set. And then in our case, you know, when you do that, you know, when you add an extra structure on X, then you can ask very interesting questions about the symmetries of X, right? Say, for example, if X is a group, you know, now you already figured out that this is actually very large, especially, you know, when the number of elements goes, you know, increases, or even when it's infinite. So this is very often very boring when you have like something like very, very big. So very often you want to just work on some, you know, narrow section of this, narrow part of it. So in a subset, a subgroup of this. So with that said, suppose that X is a group, for instance, you know, this is just a question for you. Maybe you can try to answer this in the study sessions, and then we will come to this at some point. What interesting subgroup of sim of X would be interesting to study from, say, in structural point of view, for example, if X is group, right? Why not? You know, this is a group. It happens to be a group, but we can also, the underlying set, you know, can also be a group. Why not? And another question is, suppose that X is a topological space. You know what a topological space is? This is another motivation for you for you to go and revise what a topology is. And then the question is, what could be an interesting subgroup of this sim of X if X is a topological space? Another interesting question is, now suppose that X is an n-dimensional smooth manifold. So the question is, what interesting subgroup of sim of X you would be interested to study from a structural point of view? Okay. And finally, this is relevant to the quantum guys. If X is a complex Hilbert space, well, why not? What interesting subgroup of sim of X would be interesting to study? So these are like questions that I would like you to go and think about. We will come to this at some point or the other, but just go and think about it, because we started defining this set. That's why we put it like symmetry over sets. But actually, in practice, it's not just a plain set. In practice, you deal with the structures. This could be a vector space, for instance. So, or it could be, it could be any other structure. Okay, so with that, this is the end of it. I said, very little in coverage, but I think a little bit challenging problems to try to to get your to wrap your head around the first notion. So, and I think it will be very helpful if you go through it. And yeah, that's it. The slides will be uploaded to GitHub. You can always watch the replay of the thing on the YouTube channel of the sessions. Join the Discord if you haven't joined. Follow us on Twitter and so on. Yeah. And if you see anyone who can benefit from these abstract courses, because very often, people find out late, and we already gone through part of the course, so people join late, and it's very hard for people to catch up. Very often, you don't feel motivated to to start from like behind. That's why thumbs up to Berend for he's coming after we already like 8 lectures or something, so it's not easy. So that's why try to join George, and if possible, ping someone who in the thing on the Discord, if you have anything, any doubts or something.
Yeah.
So
yes, Baron.
Yeah.
So congratulations on taking the extra effort.
Yeah, it's not easy. The thing, especially going through those live sessions, especially when you are with the others, it's much more easier to think than watching. Especially when you look at it like, oh, there's like 20 videos or something to go through. It's not easy. So commendable. Well done for that.
The stack of slides at some point looks as big as a textbook.
Yeah, yeah, that's right. Yeah. Which actually motivates me after we wrap up this crash course, to give some, maybe we should take a break, maybe a few weeks, 2 or 3 weeks or something, just to give people opportunity to catch up before we start, especially the catch up on the topologies and differential geometry side. You don't have to go through all this stuff. I mean, it helps because obviously in the topology and this is the thing, I see myself on the, let's see, return to the previous stage. I see myself on the icon and like a little icon at the top. How is this? Is this because of this? Oh yeah, so we are back again to normal. This now is the user interface in modern web companies. It's like they assume that you understand what the icons mean. So it's like self-explanatory. Yeah. So I was about to say, like maybe some Baren and some others, if you haven't taken the topology and differential geometry crash course, it is possible for you to start just from the metric spaces section onwards when we are talking about the metric topology and these things, this type of stuff, like the metric space, and then the topology induced by the metric. Yeah, but I think it's, I mean, the difference is only four sessions, I believe, anyway, from going to abstract topological spaces to actually, you know, the metric space bus, I believe. Is it not? George, do you remember?
Yeah, I mean, I think the important thing actually, again, is how to combine structures to take topological subspaces and products of topological spaces. I think that you will need.
That's right, yeah. Yeah, because without that, it will be a little bit of a more struggle to follow the Lie stuff. You might even be possible to get the computational aspect of it by watching people, you know, compute stuff and these things, especially with the concrete stuff. But in actually understanding what's really going on underneath, it's important. Yeah.
I think what might be hard for beginners is the global point of view, that there are things that true about the space as a whole that you cannot just deduce by looking locally at a small piece.
Yeah. Yeah. And there are some notions that we cover there in that, like this notion of connectedness and all this stuff.
Yeah.
That comes into play. Paths, all this. Okay, so any other questions before we end here? George, are you still okay with the study sessions, or anything has changed?
No, I intend to keep going with that, and I welcome everybody to join, because when people come into the study session with questions, it might be something I haven't thought of, so I learn something too.
Oh yeah, it's definitely beneficial to tend to attend them, because it's always an opportunity when you try to explain someone else to, and they might come up with, as you said, you know, questions that maybe you didn't think about, and then you go, this is interesting, and it's all part of the thing of getting familiarized with these things.
And if you're stuck on a challenge, it might be motivating to see that others are stuck, maybe the same way or maybe in a different way.
Yeah, that's right. Yeah, so don't feel really shy, or, you know, feel bad about it. And we all make mistakes. It's certainly, like, you know.
And also for those who, due to time zone or whatever, might be watching this on the recording later, the Discord chat is very friendly and open. I don't think it's intimidating like Stack Overflow. So feel free to ask a little question. Show, oh, this is what I've tried on the challenge, but I'm stuck here, and people I think will be very willing to help.
Yeah, absolutely. That's one of the things of the Discord. You know, please go there, and you know, and for the rest, if somebody asks a question, obviously it's a good way of you know, trying to go and figure it out, or at least point them to the right direction. You know, because you might not have time to go and write all the answers, or, you know, work them through, but at least if you can point them to the right direction, that's also already a big help. Okay, anybody wants to make any final comment before you go? I know it'll be like on the hour, so it's good to start a new topic. So, you know, let's see where this thing gets us, and maybe hopefully we can another 6 sessions we should be able to wrap this thing up. And then we are ready for the Lie stuff.
The end is in sight. We've finally got a base camp at the foot of the mountains.
Absolutely. So well done. And for those of you who have been here, like on a time consistently coming in on these live sessions and these things, you know, I'm happy to provide you the certificate again for the completion of this. So keep up going. You know, you've done very, very, very well. And this is it. We are getting there. So yeah, George, any final comment before we go? I know I keep saying any final comment and we never.
Just some thank yous in the chat.
Okay, well, thank you everyone too for showing up, and yeah, I see you in 2 weeks.
Okay, and I'll see you in 1 week.
Yes. Okay, I will set up the study session again, and yeah, I'll share it. Okay. Okay, have a good weekend, everyone. See you.